Hi friends, today in this video we're going to discuss about the moving coil galvanometer. We have to draw a moving coil galvanometer and we have to understand what are the components in the moving coil galvanometer and how it is working. For drawing a moving coil galvanometer, initially I am drawing a circle. This is not a circle, this is a cylindrical soft iron core. That is, it's like a cylinder, and we are seeing the cross-sectional view. It's a cylindrical soft iron core, and over the cylindrical soft iron core we are having armature coil wound on it, and these are some copper coils that is wounded over the cylindrical soft iron core, armature coil. And this is our cylindrical soft iron core and this is our armature coil. This is placed in a magnetic field, and the magnetic field is provided by the two concave shape magnets like this. These are two concave shape magnets. I am marking it as north and south pole of two different magnets. They are providing a radial magnetic field. These two concave shape magnets will provide a radial magnetic field. Radial magnetic field means the magnetic field, it will be directed radially or it will be directed towards the center. This is the pattern of magnetic field that this concave shape magnet is providing. And next, over the cylindrical soft iron core we are having a helical spring. It's a helical spring, and the helical spring is attached by a pointer. This is our pointer that you can see in our normal galvanometer. You can see a needle in the normal galvanometer. That needle is our pointer, and the pointer will have, or the readings in the pointer can be obtained by a scale over here. Over here it will be written 0. Let me say 10. Over here also 10, 20, 20 like this. You'll have a scale over here, and I'll mark the components. This first thing is, I'm marking it as 1. It is our cylindrical soft iron core. Can you recall what this is? The coil over here, it is called as armature coil. This is our armature coil made of copper. This is our spring. The thing which is marked 3 is our spring, helical spring. Then 4, this is our needle or pointer. 5 is scale, and 6 is the concave shape magnet which provides the radial magnetic field. Now we have drawn the diagrammatic representation of a moving coil galvanometer, and in order to understand the mathematical principle behind the moving coil galvanometer, it's a sensitive current measuring device. Moving coil galvanometer is a sensitive current measuring device. It could, or it's a current detecting device. It could detect very small currents. Initially, the needle of the galvanometer, it will be at 0 position. That is, no current is passing. And the current that is to be detected is passed through this armature coil. We are passing the current through the armature coil. If a current is passing through the armature coil, the coil is placed in a perpendicular magnetic field, as the radial magnetic field is providing a perpendicular magnetic field over the coil. Therefore, the coil will experience a torque. That is, if a current is passed through this coil, the coil will experience a deflecting torque. It will tend to move the coil in one direction. And as we have studied in our earlier expressions and all, we know the torque acting on a rectangular loop placed in an external magnetic field. It was NIAB sine phi. This was the expression that we have learned in torque acting on a rectangular loop which is placed in an external magnetic field. Since we are having concave shape magnet which provides a radial magnetic field, the value of phi in this case will be 90 degree. That means the torque will be maximum. Therefore, the torque is, we could write sine 90's value is 1. Therefore, torque is equal to NIAB. And I'm calling this as deflecting torque. This is deflecting torque. Then, since we are having a spring over here, the tendency of spring is, if there is a deflecting torque in this direction, the spring will experience a restoring torque in the opposite direction. And as we know, the value of restoring torque will be equal to, let me write K theta. K It is the spring constant or torsional constant of this spring. Theta is the angle of deflection of the needle, that is, the needle is moving from initial position to this position. This angle, that is the angle of deflection of the needle, is theta. Restoring torque is equal to k theta. At an equilibrium position, that is, if a current is passing through the galvanometer, the needle will deflect and it will settle on one position. At that position, the system is at equilibrium. At equilibrium, what will happen? The torque deflecting should be equal to torque restoring, torque at equilibrium position. Then we could write NIAB is equal to k theta. Then I is equal to k theta divided by NAB. This is one important equation that we have to study in our moving coil galvanometer. And if you are analyzing all the terms in this equation, I is the current passing through the galvanometer. K is torsional constant or spring constant of the spring. Theta is the deflection of needle. N is number of turns in the armature coil. A is the area of cross section of this armature coil. B, it is the external magnetic field density. On analyzing, you could understand that the only term which is variable is theta. All other terms are constant. Therefore, we could measure the value of current by using this moving coil galvanometer by measuring the angle theta. And I could also write I is proportional to theta. That is, by measuring the angle of deflection, we could measure the value of current. This is the expression for moving coil galvanometer. Then, in a moving coil galvanometer, we will have to learn other terms and all. The other term is current sensitivity of a galvanometer. Let me speak about the current sensitivity of a galvanometer. Current sensitivity, it is the deflection per unit current. Current sensitivity, it is the deflection per unit current. You will have a slight confusion that current sensitivity is current. No, it's not current. It is deflection per unit current. That means it is angle. The angle of deflection when a unit current is passing through the coil. It is the angle of deflection when a unit current is passing through the coil. How can we find out current sensitivity? Current sensitivity, it is obtained by the letter IS. IS can be obtained by measuring the total current, or it could be measured by measuring the total angle and dividing it by the total current. IS can be obtained by the expression theta by I, deflection per unit current. Then from this relation, can we make an expression for theta by I? It's clear that theta by I will be NAB by K. Therefore, I could write IS is equal to NAB by K. This is the expression for what? It is the expression for current sensitivity. And coming back to this equation, you could see K by NAB, this whole term is a constant. Therefore, K divided by NAB, I could write it as galvanometer constant. What is G? G is a constant that is called as galvanometer constant. It is K by NAB. It's called as galvanometer constant. Then can we correlate between these two? K by NAB is G. Therefore, I could write IS is equal to 1 by G. These are the expressions for current sensitivity that we have to learn. Current sensitivity is the deflection per unit current. Then the next thing is voltage sensitivity. Voltage sensitivity, as the name indicates, current sensitivity is the deflection per unit current. Therefore, voltage sensitivity, it will be the deflection per unit voltage. It is denoted by the letter Vs and it is obtained by dividing angle with the applied potential, theta by V, where V is potential. Then according to Ohm's law, we know V is equal to IR. Therefore, Vs is equal to theta by V. It could be rewritten as theta by IR. Can I? Then who is this theta by I? Do you know who this theta by I is? Theta by I is IS. Therefore, I could write Vs is equal to IS by R. That is, we could obtain voltage sensitivity by dividing current sensitivity with the resistance. This is the relation for current sensitivity, voltage sensitivity and current. This is the definition of galvanometer, and you will have to learn all these mathematical principles in the case of a galvanometer. Hope you have understood this derivation.